Good afternoon. It's Sunday, Mother's Day, May 14th, 2023. Happy Mother's Day. So, here as I've been reading about the differential equations. And what I've been getting into is this integration of ordinary differential equations by E.L. Ince. And what I've been getting into is these plane curves, and what I studied a little bit since yesterday was that the plane curves was really the means of exploration of the integral surfaces. I mean, these are the field lines in the usual maps, like a topographical map. These are the streamlines in a usual setup of the wind tunnel or otherwise these things. And so these plane curves are then, with regards to the isoclines, that's a lot of stuff that is still really central in dynamical modeling. But from the usual basis of the linear setups, it's a little bit left aside in the usual curriculums that provide everybody with a common curriculum and a common linear curriculum that makes it so that they have the tools that they can understand these things. And so when I studied mathematics at university, I only had a few classes or so in dynamical modeling, which even barely began to present some of these things. But at the same time, in the 1700s and 1800s, it was the milieu. And when the integral calculus was still the infinitesimal analysis, and it was, and I'm reminded of I have a book from a guy named Price from about 1900 called Infinitesimal Calculus or Infinitesimal Analysis. I found this great book. It's online. And it's out of print or out of copyright rather, and so some large outfit scanned it and put it online as either a public service or an ad traffic garnisher. I'm not quite sure what you'd say of that. But anyways, so Williamson's book is called An Elementary Treatise on Differential Equations. And it really has a lot of self-contained introduction about what we'd call today the fundamental theorem of calculus, computing the derivative, and also a bunch of the usual rules go into it, and about the substitution of variables and a lot of these things in transformation of coordinates and all this stuff that really goes a long way towards making the thing. So from reading about the plane curves, then today what happened was there was kind of like Bourbaki, or the French school about kind of rehabilitating the analysis, and then there was the Longos program or what, and so we get out of that algebraic geometry and in a sense this differential geometry, and these are still objects, but they kind of have different things, because when you look at here they just talk about only the first quadrant, only positive numbers, a function in one variable, about reflections and symmetry, about x equals y, what results at y equals x, and thus that it's possible to talk about these plane curves in the first quadrant and some analytical methods that build up on them. That's kind of what I'm thinking about when I'm kind of reviewing and studying these differential equations in the usual milieu. So plane curves had a lot going on, and so I'm happy to have learned a little bit more about that, although it did involve essentially going a couple hundred years back in the stacks to find works that were all about it and that were elementary in it, compared to the algebraic geometry and differential geometry, while still treating many of the same objects, and what results are manifolds, spaces of continuous functions, and spaces of all kinds. The Euclidean space, the Cartesian space, the Banach space, and and algebra about the complete ordered field, which is very which suffices for a lot, and it's not insufficient when you have positive and negative quantities. And that these idea of the plane curves, which as well were built up as about the Euclidean and the Cartesian are as well so parametric in terms of each other, these systems, that besides those ones that have it like x squared plus y squared equals c, the form of a circle centered on the origin, that there's lots of ways to figure out these orthogonal and the trajectories. Because essentially anything that ends up making these things are these orbits and trajectories, which basically is for making a space of the complementary duals of the orbits and trajectories. And so if the orbifold or orbital manifold, then there's something like the trajectory manifold, or I made up this word called like the trajectifold. And so the idea of this trajectifold and manifolds of the orbital really is for putting back together in a simpler space, only dealing in the first quadrant, only dealing with positive numbers, with otherwise these systems that kind of build and approach in those. Because what is left out from a lot of the systems that provide an infinite series with which you can compute as many initial terms as you have the resources and get a refinement of an answer, that also ways there's all these closed forms and solutions, and these other ones that basically make for different fundamental elements in this deconstructivist account that can help. I think that if I was really getting into differential geometry, I'd look at these as kind of like a first course, because it's not as so much as the general course, which makes a lot of these numerical methods a lot more fungible and tractable later on. But it would definitely have bridges between those at various points, which would still leave it like so and make it very well suitable for the applied. So I was thinking about y equals x and x equals y, and 1 over x and 1 over y, and those kinds of things. And and this is what I saw the other day. That would amuse me. There was this dy over the quantity root 1 plus y to the 4th, that quantity, plus dx over this quantity root 1 plus x to the 4th equals c, or 0. And well, what's that? You might ask. Well, I found this is on page 32 of Williamson's book, An Elementary Treatise on Differential Equations, and it was exercise 35. It was just like, show that this is so. But what really kind of amused me is about this displacement by 1 and this and that, because that's what I'm looking to do in terms of 1 over x and how it's symmetrical about y equals x and crosses at 1, 1. And then moving that to the origin, making this original analysis, it just struck me as one of those things that makes it in terms of the identities then, that it's possible to make these orthogonal and reflective identities about the even and odd and the symmetric and the antisymmetric to work up again in what's kind of from this non-standard framework, because I have field operations that equip -1 to 1 with field axioms that are continuous in the sense that any continuous function in the space of -1 to 1 is a continuous function in this space according to this field. And this kind of thing for an assignment that I've been really pretty happy about getting into this deconstructive account of the curriculum about the differential systems and differential equations to arrive at for this overall organization in this descriptive differential dynamics of the sheaves, topologies, submersions, the closed forms, and symmetries, and this is kind of looking at this in the symmetries, and that also this is about what was let off as the subtangent and subnormal. That was the traditional bracketing of this planar curve analysis of the 1700s, 1800s, and the early part of the 1900s, and in this book it's also referenced as well. As where they're reading from this the other day is about curves and exponential curves, and then into trajectories and the mutually orthogonal, about how it's possible to write something like the equation of a circle, which doesn't really have a function in terms of y equals f of x, except for solving the x squared plus y squared equals this constant. So when I looked up plane curves on for example, the Wikipedia, which is a first reference and resource for searching things as it's curated, and if I have a problem with it, I can submit a change to it. That there's then this whole notion of the tangent psi and cotangent psi about this 3/4, and I've been saying 3/4 rotation, but I just mean 180 degree rotation. So when I say 3/4 rotation, it's to represent 3/4 pi rotation, and about these even and odd formulas, and then about the shift of 1, and then this notion of the integration that was mentioned last time, Which is what? Which is, well, you make it so that you can compute for functions that are symmetric about x and y, where they cross x and y by A, computing the square underneath them all, and then B, computing one of the wings and just doubling that. That otherwise it becomes kind of difficult sometimes to compute in these bounds and the regions, these things. And then sort of make it up so that there's all kinds of stuff that can be resolved with this sort of 3/8 or 3/4 turn analysis. So then it gets talking to this equations of the families. Let the differential equation in the original family be f of x, y prime equals 0. And since y prime equals tan psi in the original family, and when you read tangent psi, you might want to read that as cosine over sine, or sine over, as with respect to tangent. I always forget the opposite over adjacent and the opposite over hypotenuse and adjacent over hypotenuse. So the cosine over sine, and then the cotangent it's reciprocal and inverse. In terms of cosine and sine, that later it's just as those are orthogonal functions about the tangent and line and the normal line at the curve are perpendicular and so on. About as when sine and cosine cross, that they cross at right angles. Anyways, since y prime equals tan psi in the original family, f of x, y tan psi equals 0, since y prime equals tan psi. Or again, f of the quantity x, y, and then this quantity, tan psi 1 minus m, this intercept, over the quantity 1 plus m tan psi 1 equals 0. But in the family of oblique trajectories, y prime equals tan psi sub 1, and therefore this family consists of the integral curves of the differential equation, f of x comma y of y prime minus m over 1 plus m y prime equals 0. Now when you have this kind of on or off by 1, this is something that might be familiar to a lot of people if they're used to computer programming and the development of algorithms that affect according to the array offset indexing, which is usually in the languages of this day, they're 0 based, because that way you can reference a memory location by its value, and then increments or differences from it are as from 0, compared to like in the first box is 1's box or something like that. Then these off by 1 errors end up being stuff like, oh, well, then when you come around and you're doing it from the previous and the next or something like that, there's an increment and it takes place some point in the algorithm, and it's like so. But here it's kind of like sometimes it looks like what variable are we dealing with? Well, we're dealing with 1 plus x minus 1. What kind of quantity is that? Well, it's a quantity that you can't cancel 1 and negative 1 until such time as you made it so that it's matching the other side, because x equals y. And in these kinds of things. And so it gets into the quantities that are, and in the algebras and arithmetics, and this has been part of the talk in the analysis and methods talks quite a bit, but also just in terms of the quantities in algebra, and that arithmetic is different than algebra. And arithmetic of plus is different than arithmetic of division, and they go together. And then arithmetic and algebra go together. But when they do, then the quantities are sort of defined under those. But there are other algebras where it's not so. And there's other arithmetics where it's not so. And sometimes those are the ones in effect. For example, here in this deconstructivist account, there's just this positive numbers in the first quadrant. And then if you want to deal with a whole half plane of those, then the idea again is to rotate that so that x equals y is as of going to the right, and then expand that and interpolate all the points in between so that then what was the x-axis and the y-axis go north and south from the origin. And then the east or to the right is this half plane or the analytical region. But here we're just keeping things reduced to the first quadrant and rotating that 3/4 of a turn, a turnaround, a half turn. But that then this triangle, which is having its apex in the origin of the quadrant, is on top, and then the base is as a projective perspective out at infinity. and bring that in this non-standard analysis. So here when I look at this differential equation, and it has like the terms of this constant, and then its terms of this offset by 1, that's what I'd be looking to do to figure out in terms of these quantities, and where we're in a restricted setting of the algebra and the arithmetic until we get back down to it, that then it places that back out as y 1 plus x minus 1 equals x. But in the derivative, in the derivation of the formulas and their manipulation, and their substitution with identities and their exchange of reflections and symmetries and and things are even and balanced about them, that's a thing. Going on here, if therefore the differential equation of a family of plane curves is known, see, this is where the differential equation has many solutions, but many plane curves share one differential equation. The differential equation of the family that intersects it at a positive angle omega is obtained by replacing y prime whenever it occurs by y prime minus m over 1 plus m y prime, where m equals tangent omega, or what is the same thing, by replacing dy by dy minus m dx, and also dx by dx plus m dy. So this is one of the biggest things about why it's solved the other way, because the raw differential, or the bare differential, or the naked differential, the differential by itself, and that leads to ambiguity because it's a quantity, and so if it's left out in terms, just like we've been talking about, these quantities must be preserved, and the operations as about them and their arithmetics and algebras must maintain these relations, but we want it to do so in their numeric and symbolic values without much otherwise attachment to other objects or variables in the equivalence classes of same. These are the kinds of things we get into, and looking at why this whole kind of approach from the plane curves and their differential functions, and then the differential functions and their solutions, and finding solutions given values, are these complementary duals. So we're getting back to complementary duals and a whole idea that the whole study of differential analysis is at least two things. It's solutions and it's curves. For differential equations and as differential equations. Let f of r theta alpha represent a one parameter family of planar curves and polar coordinates, and let the differential equation of the family be f of r theta quantity dr over d theta equals 0. So dr d theta is the rate of the radius with the rate of the angle. So if you draw a spiral and the radius equals the angle in terms, and it just goes out and about, and then each time that you it's not just a modular clock angle that goes from 0 to 2 pi and starts over, but it goes to 0 to 2 pi to 4 pi to da. It has, this is kind of like k, the term the other day, and like the kth period of the periodic function, and the near field is 0 to 2 pi, and the far field is when it goes out for these things. And let r theta be any point through which a curve passes, and let theta be the angle which the tangent at that point. And then we got to keep in mind that his tangent is with regards to the tangent that has an intercept that crosses the origin behind. It crosses back behind the origin. That this tangent crosses the y-axis, and then later it meets the x-axis, and because here we're dealing with the positive quadrant, and then that where the ordinate drops to the x-axis, that makes a triangle, and that then where the normal connects to the y-axis makes another triangle. This is kind of how it's set up. And let phi or phi be the angle which the tangent at that point makes with the radius vector. So the radius vector would be from the origin to the point there. So that tangent phi equals r of d theta over dr. Instead of dr over d theta, it's d theta over dr. An oblique trajectory of angle omega will be such that the angle which its tangent makes with the radius vector will be phi sub 1 equals phi plus omega. And we have tan phi equals tan quantity phi sub 1 minus omega. So for theta, there's phi as of about this angle omega. Theta is the usual polar coordinates angle. And this phi is in terms of phi plus omega, this other angle, and tangent of phi equals tangent phi sub 1 minus w equals all this quantity read out. In the numerator, tan phi sub 1 minus tan omega over the quantity 1 plus tan phi sub 1 tan omega, that quantity, equals r d theta over dr minus m over the quantity 1 plus mr d theta over dr equals r d theta minus mdr over dr minus mr d theta. And that's one thing with this arithmetic and the differential quantities is that it's almost always easier when they're products, because that means that over above and below the divisor bar, those cancel. But when they're sums, then they grow in their products, all the sums, and you get all the polynomial, multinomial, and get into the hypergeometric and stuff like that. But these kinds of things, then, with regards to something like the Matthew function, M-A-T-H-I-E-U, Matthew function does not have a hypergeometric representation. Oh, really? Yeah. Well, it's very very much interesting, and it's kind of unique. And among these things about the multinomial, polynomial, and the hypergeometric, that it gets to then for what families of functions arise, and families of coefficients of polynomials in the algebraic, and these things make for solutions of so that they have for simple definitions of functions and these families of plane curves, simple definitions of their differential functions, and simple definitions of those having solutions, and differentiating and integrating them, computing the gradient, and implementing mensuration will be such, thus the differential equation of the oblique trajectories will be obtained from that of the original family by replacing r d theta by r d theta minus mdr, and dr by dr plus mrd theta. In the case of orthogonal trajectories, we would have phi sub 1 equals phi plus minus 1/2 pi for the orthogonal trajectories, or tangent of phi sub 1 equals negative cotangent phi. So this is sort of even odd bit, because for the reciprocals, sine and cosine, the opposite is cosine over sine, and then it's negative that, equals negative 1 over r times dr over d theta. So that r d theta is replaced by negative dr and dr by r d theta. This is, again, this notions of the complementary duals and the anti-symmetry are what makes these orthogonal functions. This is a pretty great thing. So, example 1, the equation x squared plus y squared minus 2ax equals 0 represents for varying a all circles which touch the y-axis at the origin, center of any individual circle being a, 0. Its differential equation is x squared minus y squared, that quantity dx plus 2xy dy equals 0. To find the equation of the orthogonal trajectories, replace dx by dy, dy by negative dx, x squared minus y squared dy minus 2xy dx equals 0, which is really the same equation with x and y interchanged throughout. Now, this is pretty great. It's really the same equation with x and y interchanged throughout. That's the whole idea of a lot of these other functions, that these sort of isoclines in the positive numbers about being symmetrical about x equals y, is that they're all of this sort. So they're only positive numbers. In a sense, there's a space of only orthogonal functions. And those make a lattice grid. That the lattice grid itself is the first set of those, the integer lattice. It's pretty great. Interchanged throughout. Its general integral, therefore, is x squared plus y squared minus 2 beta y equals 0. So he's able to replace dy by 1 and x dx by beta, so that the orthogonal trajectories are all circles which touch the x-axis at the origin. Example 2, it may happen that any one member of a family intersects at right angles in an infinite set, not necessarily all of members of the same set. Such a family is said to be self-orthogonal. Oh. Any one member of a family intersects at right angles in an infinite set of members of the same set. Such a family is said to be self-orthogonal. For example, consider the family of confocal parabolas. Y squared equals 4c of x plus c, i.e. parabolas with a common focus at the origin and common axis 0x. So the focus of the parabola is like 1, 1, right? Because all the angles that fall down into a parabola all reflect and hit the focus. That's what a parabola does, like a parabolic mirror, solar oven. That's how it works. And so we have, and this is one of these facts that makes for that is well known. That also makes for like how to build that elementarily. Well, it's tough, but it gets into making a way to implement that, and I'll be interested to find out more about it. But it's one of these properties of these well-known curves. It's after parabolas, hyperbolas, and ellipses, maybe, are out of conic sections. So anyways, going on, and circles, if not ellipses though, but parabolas and hyperbolas and circles. Conic sections. We have y times dy over dx equals 2c, and eliminating c, y equals 2x of dy over dx plus y times the quantity dy over dx squared, or y of the quantity dy squared minus dx squared plus 2x dx dy equals 0. And again, I'll need to look back at these encompass then a lot of these methods that went into the manipulation after the vanishing variables that take the product after implementing the function as finite differences, multiplying that out, dividing it by such, the finite difference, or h, and then as that goes to 0, and then discarding evanescent terms, or what, so treating the differential and the rod naked bare, or the differential without further qualification as algebraically. Again, that gets into these systems of quantities, and when and where quantities are conserved and preserved, and when and where arithmetic and algebra apply, and when otherwise they do not, and especially when they do not, and also their anti-applies, so that they actually have real character on the other side. The differential equation of the family of parabolas, remains essentially unaltered if dy is replaced by negative dx and dx by dy, so that the family is in fact self-orthogonal. Now, again, this is kind of under-justified, because what it needs to be, because they're always, to be orthogonal, the vanishing quantities, they always need to be in ratio. But here's establishing, that you can substitute them in terms of each other, because x equals y is really, or as he put it in the previous page, really the same equation with x and y interchanged throughout. This is very principal in the methods, and so it's going a long way towards helping me understand some more about the complement of a differential equation defining superposition and of solutions in a family of solutions, and a family of plane curves identifying to a differential equation, and then particularly when there's various of those, because we need existence and uniqueness results, then we need to kind of have something that makes for the definite over the indefinite, and we have to watch out for indefinite quantities, which I mentioned as 0 over 0, but include anything that's about 0 over 0, or infinity, or 0 over infinity, or infinity over 0. That going on, this family of parabolas remains essentially unaltered if dy is replaced by negative dx and dx by dy, so the family is in fact self-orthogonal. To see how this property originates, consider the two particular curves. Y squared equals 4a of quantity x plus a, and y squared equals 4b of quantity x plus b. Their point of intersection has the abscissa x equals negative quantity a plus b, and the ordinate is given by y squared equals negative 4ab. So the abscissa and the ordinate, in terms of how they attach to the axes, these functions by the coordinates, are primary in the sense, and also with the subnormal and the subtangent and the and these things. So the ordinate is kind of the intercept because it's negative 4ab, as you expect from the derivative of x squared. And the other one is, as of arithmetic, the difference there where they meet. Thus, the intersection is real only when a and b are of opposite signs. Because otherwise, it has a y squared equals negative 4ab. So, as we've been talking about, only dealing with things in the positive, it's one thing, but also he says this real field, in terms of the roots of negative numbers, always extends to the complex field. Here, that he's noting that these are the only real solutions, only when a and b are of opposite signs. So similarly, we'd look at similar things when there's only positive solutions. When that, and in terms of what's the complement to x squared, then, well, it's x to 1/2 or something like that. Thus, the intersection is real, and when that is the case, the gradients of the two curves at the point of intersection are respectively either root of the quantity negative a over b and negative root of the quantity negative b over a, or negative of the quantity root of the quantity negative a over b and root of the quantity negative b over a, which verifies their orthogonality. Is just like about the evenness and oddness and this kind of stuff. So these kinds of things really can help a lot, it seems, to keep things square over the course of these curves by their derivatives and finding their derivative functions and the differentials as about the differentials. So when we say differential, it pretty much means Leibniz's differential, who is considered one of the discoverers of the integral calculus. When that is the case, the gradients of the two curves, which verifies their orthogonality. Example 3, to find the oblique trajectories of the family of straight lines y equals ax, the differential equation of the family is xy prime equals y, or x dy equals y dx. And so here we've been talking about like x equals y and y equals x equals 1 over y, and y equals 1 over x. And here we have x dy equals y dx. And this is the differential equations of straight lines that go through the origin. And therefore that of the trajectories, x of the quantity dy minus mdx plus y of the quantity dx plus mdy, or x dy, distributing multiplication and then putting on either side of the function, putting the like terms on the same side of the function, or x dy minus y dx equals m of the quantity x dx plus y dy. Clearly, this is a case for a change to polar coordinates. Oh, really? Which gives r d theta equals m dr. The general integral is r equals beta times e to the theta over m. So here's the first introduction of the exponential of this general integral of same, i.e. the trajectories consist of a family of equiangular spirals. Well, that's remarkable. I am always interested about the linear and about the space-filling spiral curve, which is the idea that you start at the origin and the only way it connects the dots is it is constantly just increases in dimension and until it has to increase in distance. So you go out through however many dimensions you're considering. And for example, a straight line or in 0 dimensions, it's like next dot, next dot, next dot, drawing that line out between 0 and 1. But in 2 dimensions, it looks like a spiral. But here in this plane, straight lines as orthogonal trajectories are like so. So that seems very natural. In polar coordinates, the family of circles in example 1 is r equals 2 alpha cosine theta. Its differential equation is is dr equals negative r tan theta d theta. The orthogonal trajectories, which are the integral curves of r d theta equals tan theta dr, are the family r equals 2 beta sine theta. So here I'd be liking to take this approach to the planar curves about the opposite over adjacent and of the normal and tangent in terms of the abscissa and ordinate of trying to figure out how to, in terms of tangent being sine over cosine, finding out what else essentially represents tangent or cotangent as a quantity without sine and cosine, or as, for example, a system, or as a series, because I'd like to know more about that. So section 16 in this integral curve starts level lines and lines of slope on a surface. Let this surface be referred to a rectangular system of axes with the z-axis vertical. The xy plane will be the horizontal reference plane. So we have it's kind of like a topographical map, and the isoclines indicate some value or something like that. The section made on the surface by a horizontal plane z equals a is a level line or contour line of level a. The horizontal projections of the various level lines made by a regular sequence of horizontal planes z equals a1, a2, form a contour map. If a is varied continuously as it does on the secant plane, so cosine, sine, secant, cosecant, with the inverses in that, it moves uniformly upwards, and then I need to understand what secant plane means, because this was not very much brought out as the usual apparatus in geometry, but it's defined, but it's specific here. Moves uniformly upwards, the contour map is replaced by a family of curves in the xy plane dependent upon the parameter a, or alpha. If the equation of the surface is fxyz equals 0, those curves will be contained in the equation fxy alpha equals 0. The lines of steepest slope on the surface are the lines of minimum distance between successive contours. So this very well reflects the notion of the gradient, that the more of these level lines or streamlines or isoclines or field lines there are in a region, the denser those are, the steeper it is through those, because a shorter line is able to cross more of those, thus being steeper. So this is as of computing the gradient in the plane instead of the partials as about these lines, by finding the orthogonals and dropping down through that. And then of course the partials are either that in terms of the vectors and But finding those, because then you'd have a parametric form in one variable or along those lines for those. And that would be great. And are therefore lines cutting the level lines at right angles, on account of the fact that when two curves in space, one of which lies in a horizontal plane, cut orthogonally, the horizontal projections will cut orthogonally. We see that on the horizontal reference plane, the projections of the lines of steepest slope are the orthogonal trajectories of the contour lines. I.e., if any given contour line at any given point has its orthogonals coming out of it. And then the ones of those that connect with the shortest bend and the least bend and the shortest distance kind of put together are which way the wind blows and where the water flows. The fall line, which is the fall line is that according to least action, that's the way to go to achieve the highest velocity in the alpine skiing. We see that on the horizontal reference plane, the projections of the lines of steepest slope are the orthogonal trajectories of the contour lines. If the equation of these trajectories is g of the quantity, g of xy beta equals 0, so the trajectories are xy beta and the lines are f x y alpha, the lines of steepest slope on the surface will be the intersections of the surface by the cylinders gxy beta equals 0, whose generators are parallel to the z-axis. So that basically has that x and y are partial in z, that this cylinder is dropping in z, generators are parallel to the z-axis, so that it's kind of like anywhere in the map there's a cylinder, and that's called here a generator. He says, example, consider the parabolide 2z equals ax squared plus by squared. The level lines project into the family of curves ax squared plus by squared equals 2a, whose differential equation is ax dx plus by dy equals 0. The orthogonal trajectories, whose differential equation is ax dy minus by dx equals 0, will be found to be y to the alpha equals beta x to the b. Or excuse me, y to the a, beta x to the b, and hence the lines of steepest slope may be found. Well, in particular, when a equals b, i.e. in the case of a paraboloid of revolution, the lines of steepest slope are the intersection of the surface by all planes to the z-axis. That is, they are meridian lines on the surface. So this there is some definition of whether the longitude and latitude lines or here are the meridian lines, and they reflect well on our notion of the globe and how that's spinning. It's pretty interesting. And then it gets into singular points. Now, singular points will be something for all these kinds of things to get figured out. And it's pretty cool. That points at which the gradient becomes indeterminate through the simultaneous vanishing of P and Q are said to be singular. And so this is the same thing in the PDEs as here. When there's singular points or cusps or what, they got to get figured out. Thus, singular points are the points of intersection of the curves Pxy equals 0 and Qxy equals 0, which are the loci of points at which the integral curves have tangents parallel to the x-axis and the y-axis respectively. They are thus in general isolated points. Or are their surfaces? Well, that's pretty interesting. So this little book has a lot then a lot of this other stuff is brought up above it and build that way out. So that'll be something more we'll get into as this goes on. Well, have a great day. I'll be interested to learn more about these plane curves and putting together the submersion symmetries and sheaves of the plane curves subfunctions, as we'll get into this holistic approach to differential analysis as a whole and the ability to look at things from each of the ways, so that when there are the presence of complementary duals in arithmetic and algebra and quantities and equations, that they're resolved satisfactorily. Hey, great. Have a great day.